Hello, Physics 2 students. In this video, I want to talk about the idea of mutual inductance as well as describe what happens inside a transformer. So we've already talked briefly about mutual inductance. Mutual inductance is when one loop or coil has a time-dependent current, which creates a time-dependent flux through a second loop or coil, and that second loop or coil gains an EMF. So in particular, we want to understand the EMF, say in wire 2, and how it's related to the current flowing in wire 1. And the relationship is using mutual inductance. Okay. Not too surprisingly, for linear materials, we can dispense with the derivatives and we can simply say that rather than saying well, instead of using calculus, we can rewrite this and say mutual inductance of 2 on 1 is simply the flux through loop 2 divided by the current 1. And similarly, for mutual inductance of 1, or of 2 through 1, you just swap the labels. So let's go through this process for a solenoid here, where I've got two wires that are kind of wrapped. They're kind of against each other. They're sort of counterwound. So in that case, well, if I have many, many turns, I can think about wire 1 as giving me a solenoid magnetic field. So that's just going to be mu naught times the number of turns in wire 1 times I divided by the length. Oh, I'll write that with a lowercase l. The length is on the other hand, the magnetic flux through loop 2 is going to be N2 times the magnetic field coming from 1 times the area of loop 2. So pulling these little facts, this should have been the current through 1. Pulling all these little facts together, we get that the magnetic flux through 2 is equal to N2 times the current times the area of loop 2, which is the same for both of them because it's a cylinder, times the magnetic field from 1, which is going to be N1 mu naught times I1 divided by L. So I can rewrite that as N1 into mu naught A over L times I1. The mutual inductance of 1 on 2 is phi 2 divided by I1 is simply going to be N1 into mu naught A over L. And you'll notice this final result is completely symmetric between 1 and 2, and it turns out the mutual inductance of 1 on 2 is the same as mutual inductance of 2 on 1. They're the same. Okay, so that's how you calculate mutual inductance. The last thing I wanted to do in this video is to talk about a transformer. And in a transformer, you have two coils, and rather than kind of co-winding them, oh, before I move on to transformers, let me also say one thing. The minus signs in the formulas I had are intimately tied to the way that these wires were wound. And if you were to reverse one of the wires, you would simply pick up a minus sign. And that's exactly the dotted or undotted notation that you had in linear electrical circuits. That's exactly telling you how to choose minus signs, which means you're telling you how you've wound the various coils. All right, so let's come back to transformers. So in a transformer, a lot of times we don't counterwind the coils because it's easier to simply start with a chunk of metal, say iron, and then wrap it over here and wrap it over here. And we'll say we have N1 times here on the left. And we'll also have N2 times over here on the right. And by using a piece of metal, remember, field lines would much prefer to follow the iron all the way around rather than leak out into the room. So that means that essentially every field line which passes through one loop of coil 1 will also pass through one loop of coil 2. So if the number of field lines that goes through each of the separate coils or turns on the left is equal to the same number of field lines which pass through each turn on the right, we learn the following, that the one turn result from the left must equal the one turn result on 2, or rather than thinking about one turn, we can simply think about the entire flux on the left and the entire flux on the right, and then we can erase this condition by simply dividing by the total number of turns, where phi 1 and phi 2 refer to the total flux on the left and the total flux on the right. But, if you take a time derivative on both sides, we can conclude that the EMF of 1 is going to be N1 over N2 times the EMF across 2. So this is a transformer. We can change the EMF. So by adjusting the ratio of turns on the right versus left, you can either step up or step down the voltage difference across the transformer, across this inductor. All right, so that's what we do, or that's how transformers work. It's the essence of it. All right. In the next video, I want to talk about the energy stored in a magnetic field.